Welcome everyone to lesson 2.4 from Precalculus, which is all about exponential function manipulation. So we were taking those exponential functions we've been talking about, and we're going to manipulate them through transformations here today. So to start things off, let's recall some properties from Algebra 1 and Algebra 2 regarding exponents. So the first property we're going to talk about is the negative exponent property, which means that if you have something to the negative 1 power, that is essentially taking the reciprocal of it. So if you have 2 to the negative 1 power, it would be taking the reciprocal, it would be 1/2. If you have a fraction, like 3/2 to the negative 1 power, well, the reciprocal of that would be 2/3. If you have -2, -3, -4, -5, you take the reciprocal and then you can apply the power. Or you can apply the power and then take the reciprocal. So for example, 2 to the negative 3 power would be 1/8. The product property. So the product property is where you have two like-based exponentials and you multiply them. And when you do so, you can just add the exponents together. So 2 to the third times 2 to the second is equal to 2 to the fifth. Quotient property is the opposite of that. So it essentially combines the negative exponent property and the product property into a singular property, which is if you divide two like-based exponentials, you can just subtract their exponents. So 2 to the third divided by 2 to the second is 2 to the first. It makes sense, especially when you start plugging in numbers to try to verify these or make sense of them in your own brain. They work. The last one we're going to talk about is the power property. If you have an exponential raised to a power, it is the same as multiplying the exponent of the exponential with the new power. So 2 to the third to the second power is equal to 2 to the sixth. Not too bad. All of that should be old news. How does that relate to what we're doing? Well, we are transforming exponentials. So the first transformation we're going to talk about is horizontal translations. So that is where we add or subtract to the input of a function, right? So we're doing f of x plus k, essentially, to translate. If we add a positive k, that moves it left. If we add a negative k, then it moves it right, so on and so forth. So for exponentials, the input is the power. So if we have f of x equals b to the power of x plus k, well, through the product property, we can use the opposite version. Instead of going forwards, we can go backwards, which is perfectly fine, equivalent, right? We would get b to the power of x times b to the power of k. Well, b to the power of k, doesn't matter what b is, doesn't matter what k is, that's going to be a constant. We don't know what that constant is. It could be anything. It could be 5,712,000. We don't really know, but it's a constant. So for our intents and purposes, let's replace it with a. So b to the k is equal to a, and that gives us f of x is equal to a times b to the x. What does that mean for us? What does that imply? Well, that implies that exponential functions have a unique property that horizontal translations and vertical dilations are equivalent. They are the exact same. How you go about them and the increments needed to produce the same result may vary, obviously, but shifting it horizontally is the same thing as stretching it vertically. So I've got some examples graphically, so you just don't have to take my word for it. So the first one we have is 3 to the power of x. If I shift it to the left 2, which means that I add 2 to it, I get this orange function here. But if I multiply 3 to the power of x by 9, I get this purple function. And we can look and verify that they share all of their points, and by sharing all of their points, they therefore are equivalent. So that's nice, that's cool. How does that relate? Well, 3 to the power of 2 is 9. We can also work the other way. So 2 to the power of x would be this nice blue function in the bottom row. So if I have 2 to the power of x minus 3, I'm shifting it to the right 3. Well, 2 to the negative 3 power is 1/8, so that's the same thing as multiplying 2 to the power of x by 1/8. And we can verify again through equivalent points that we get the exact same function, which is pretty cool. So if we are given something that is a vertical dilation, we can rewrite it or describe it as a horizontal translation. Well, look at what we're asked to do next. So we're going to let f of x equal 3 to the power of x, and we have two functions that are described as a vertical dilation. We're going to instead describe them as translations. So what we need to do is we need to modify this so it looks, instead of like the rightmost column here, like the middle. So we're going to use properties of exponents to do so. I know that 3 to the power of 2 is 9, 3 to the power of 3 is 27. So that's good. So 3 to the power of 3 is 27. It's in the denominator, so we can rewrite this as g of x is equal to 3 to the negative 3 power times 3 to the power of x, which means that g of x is equal to 3 to the power of x minus 3, which means that this is a horizontal translation, and this would be right 3. And we can say units. We don't really know what it is. It's good to get in the habit of writing that. So the next one is 81 times f of x. Well, we know f of x is 3 to the power of x, so I can go ahead and rewrite that. Problem's trying to be cheeky, I guess. So 81 is also a power of 3. 3 to the power of 3 is 27, but if we take 27 and multiply that by 3, we get 81. So 81 is just 3 to the 4th power. So we can rewrite this as 3 to the x plus 4, which means this is a horizontal translation. And this would be left 4 units. Not too bad. So we dilated vertically. What about dilating horizontally? Well, let's look at that and use powers of exponents to examine that behavior. So if we have b to the power of a times x, that is essentially the same thing as b to the a to the power of x through the power rule. Well, b to the power of a, well, b and a are both constants, so b to the power of a is just a constant. Let's call that constant big B. So we have f of x is equal to big B to the power of x. What did that do? Well, all we did is we modified the base of the exponential. So vertical dilations just means that we're changing the base of said exponential, which means that all exponentials are dilations of one another, which I think is really cool. So graphically what that would look like is 2 to the power of x is our default function. 2 to the power of 2x would be this nice orange function here, and 4 to the power of x is this nice purple function. But if we look at the points, they match up. So those functions are equivalent, which is kind of cool. So let's do kind of like what we did before, and let's take 3 to the power of x and describe some transformations as dilations, in this case, of 3 to the power of x. So the first one, we have 9 to the power of x. Well, 9 is just 3 squared. So we have 3 squared to the power of x, so that means that we have 3 to the power of 2x, which means that we have a horizontal dilation by a factor of 1/2. Remember that when we're dealing with horizontal transformations, that it's always the opposite of what we think. So we're multiplying by 2, we're actually having that time needed. Then we have the one that's a little cheeky like the other one, where we have an f of x instead of the function itself. So let's go ahead and replace that. So we have 3 to the power of x to the power of negative 3. Well, that would be 3 to the negative 3x. So we actually have two things going on here. We have a horizontal dilation by a factor of 1/3 this time, but we also have that negative. What does that negative do? It's reflection. Reflection over what? It's affecting the input, so it's a reflection over the y-axis. How many people remembered that one? If you did, good on you. So the last thing that we're going to talk about in this lesson is radicals. So not sure how much this was taught in Algebra 2 or Algebra 1 for you all, but if you have a fractional power like x to the power of a divided by b, then we can rewrite that as the bth root of x to the power of a. We do have to keep in mind that if b is even, its domain can only include 0 and positive numbers. No negative numbers can we use there. So if b is 2, if b is 4, if b is 1000, we can only have positive numbers in the input of a radical. Do keep in mind also that a square root, which is a 1/2 power, we don't have to put the 2. So let's finish off our last question here by evaluating some functions with fractional powers. So what I'm going to do is I'm going to substitute in first, so 2 times 5 to the 1/2. 5 to the 1/2 would be the square root of 5, so 2 square root of 5, and that's all we need to do. There is no more to be done. We can find a decimal approximation, but most of the time if you have a problem like this, it's best to leave it in its exact form. Now if we could simplify the radical of 5, we would try to do that, but for now, that's all we need to do, and if you have questions on simplifying radicals, make sure you ask me. Last but not least is a weird one. So we want h of -2, so 6 times 2 to the -2/3 power. So that is 6 times the cube root of 2 to the -2 power, which reciprocal, so let's go ahead and actually reciprocal that now, 1 over the cube root of 2 squared. We know what 2 squared is, that's 4. So this is 6 times 1 over the cube root of 4, or we can just rewrite that as 6 over the cube root of 4, and that is perfectly fine. Now, this brings in a little bit of a weird situation that we'll have to talk about, which is it's not proper to keep radicals in the denominator of a fraction. Mathematicians just don't like it because there's countless ways to represent radicals that way, and it's best to have the most simplified form whatsoever, which mathematicians have determined that means radicals in the numerator. For right now, that's okay, especially with one as weird as that, because I have an explanation down here of what that turns into, and it's kind of ugly, I'm not going to lie. But when you have a radical in the denominator, it is proper to rationalize it. What that means is you're going to multiply it by its conjugate. So if I have 1 over the square root of 2, very, very important for trig, I can take that 1 over the square root of 2, multiply that by the root 2 over root 2, and that gives me a final answer of the square root of 2 divided by 2, or root 2 over 2. Our answer we had before is a little bit different, because the cube root of 4 is the same thing as 4 to the 1/3 power. So instead of multiplying it by itself, you'd have to multiply it by 4 to the 2/3 power to get the denominator to be 4 to the 3/3 power, or 4 to the 1st power. And you get 6 times the cube root of 16 over 4 as the proper answer to our last question. Make sure that we simplify our radicals nicely and rationalize them. That is it for this lesson, so if you have any questions, make sure you ask. Otherwise, I'll see you in the next lesson.